Hi, so in this video we're going to review Chapter 5. So open up your books, so get your book out. And on page 253 of the textbook is the beginning of Chapter 5, okay? So Chapter 5 is on inverse functions. Alright, so the chapter starts off with an example of an inverse function. And you see an arrow diagram here on the left depicting one function and its inverse. Okay, so some functions have inverses and some don't. Okay, it gives a definition of a one-to-one function. Right, a function is one-to-one if it never takes on the same value twice, and that is f of x1 does not equal f of x2 whenever x1 does not equal x2. Okay, top of page 254. Then it says a function is one-to-one if and only if no horizontal line intersects its graph more than once. Right, so if you had this function, right, it's one-to-one because no horizontal line intersects the graph more than once of that function. If you had this function, that's not one-to-one because there is a horizontal line that intersects the graph more than once. And so this semicircle is not a one-to-one function, and that is a one-to-one function by the horizontal line test. All right, so that's horizontal line test. Okay, it gives a definition of an inverse function at the bottom of page 254. Then, right, so the equation for an inverse function is f inverse of y is equal to x if and only if this is in other words for if and only if f of x equals y for any y in B, the domain of f inverse. A is the range of f inverse. Okay, so what this means is that f inverse is a function that if you take, let's say, y as your input, f inverse would map, let's say, y to x if and only if the function f maps x to y. Okay, so that's the relationship between f and f inverse. They're kind of like opposites of each other. Okay, and so some functions f have an inverse and some don't. We know that f is one-to-one. When f is one-to-one, that means it has an inverse. Okay, the domain of f inverse is the range of f, and the range of f inverse is the domain of f. Okay, so that's stated at the top of page 255. Okay, we also have the cancellation equations. F inverse of f of x is equal to x for every x in A, domain of f, and f of f inverse of x is equal to x for every x in the domain of f inverse. Let's say for every x in B. And so these are called the cancellation equations for f and f inverse. Okay. Okay, just check over the video. Okay, so these are called the cancellation equations. Right, so, and then on page 256, there's a three-step process defining the inverse function of a one-to-one function. Step 1, write y equals f of x. Step 2, solve the equation for x in terms of y if possible. And step 3, switch x and y, and the new y is f inverse of x. Okay, so that is the three-step process for finding the inverse function of a one-to-one function f. It's on page 256. Okay, we went over it in class. Okay, also, if you have the graph of a function f, right? Let's say you have the graph of a function f, and it looks like this. If you want to know the graph of its inverse function, right? This is a one-to-one function because the horizontal line test, since there's no horizontal line that intersects the graph more than once, it's one-to-one. And so this is the line y equals x. So when you reflect this graph about y equals x, you get a graph that looks like that. And then this is the graph of y equals f inverse of x. Okay, so if you reflect the graph of a function about the line y equals x, for an invertible function, the graph of the reflection, that is the graph of the inverse function. Okay, and so that's mentioned on page 257. Okay. At the top of page 258, it says, right, if f is a one-to-one continuous function on an interval, its inverse function is also continuous, so you should know that. Theorem 7 on the page. Theorem 7. Theorem 7. If f is a one-to-one differentiable function with inverse function f inverse and f prime of inverse of a does not equal 0, and the inverse function is differential at a and, okay, so I won't require you to show those conditions hold, but you do need to know this equation and when to use it and how to use it. Have an idea of when to use it, okay? Without worrying about the complete justification of it. You have this equation here, okay? This is called the inverse function theorem. So f inverse prime of a is equal to 1 over f prime of f inverse of a. Okay, so you need to know that equation. All right, and so that is a summary of 5.1. All right, because that's summary of 5.1. Now if we look at 5.2, it defines the natural logarithmic function. Right, the natural log function is defined as ln of x is equal to the depth interval from 1 to x of 1 over t dt for x positive. Okay, that's the definition of the natural log function. Okay. Also, on the next page, page 262, right, you're given a ddx of ln x is equal to 1 over x. Okay, you have the three laws of logarithms. You need to know the three laws of logarithms. Ln of xy is equal to ln x plus ln y. Ln of x over y is equal to ln x minus ln y. And ln of x to the r is equal to r ln x. Okay, so these are our three laws of logarithms. So often in class I would label an equal sign with 1, 2, or 3 to denote which law of logarithm I used to justify that equality. Okay? So the limit as x approaches infinity of ln x is equal to infinity, and the limit as x approaches 0 to the right of ln x is equal to negative infinity. Those are also important limits you should know. Okay? Okay, you need to be able to expand logarithms using the three laws of logarithms. You need to, not only do you need to know that ddx of ln x is 1 over x, you need to know that ddx of ln of a function of x u is equal to 1 over u times du dx. That's the derivative of ln of x combined with the chain rule. Okay? U here is a function of x. You also have that ddx of ln of the absolute value of x is 1 over x. So this is for only x positive. ln x is only defined for x positive, right? But here, for ln of absolute value of x, this is any real number x. Ln of absolute, any non-zero x. Okay, so now we'll define a non-zero. So this, we can define the ln of absolute value of x on every non-zero x. That's the advantage of this equation for that one. Okay? And so, since we have this equation, we also have the integral of 1 over x dx is equal to ln of absolute value of x plus c. Alright? So you need to know that also. Right? Those are 4 equations you should know. Also, at the end of the chapter, they mention that the integral of tan x dx is equal to ln of the absolute value of secant x plus c. So that's equal to. Okay, and then there's one in the middle of page 267. There's logarithmic differentiation. You need to know how to do that. Okay, and there's the 3 steps for logarithmic differentiation on page 268. Okay, so you take ln on both sides of an equation y equals f of x and use laws of logarithms to simplify. Step 2, differentiate implicitly with respect to x. Step 3, solve the resulting equation for y prime. So those are the 3 steps, and they're on page 268. Okay, so that's 5.2. That's 5.2. All right. Okay, so that's 5.2. So for 5.3, defines a natural logarithmic function. Okay, so y equals ln x we had in the previous section. Y equals e to the x is proved to be the inverse of that function. Okay, and so e to the x equals y if and only if ln of y equals x, because e to the x and ln are inverse functions of each other. And so you get cancellation equations. E to the ln x equals x, and ln of e to the x equals x. This is only for x positive, because ln x is only defined for x positive. This is for all x, all real numbers x, because e to the x is defined for any real number x. And e to the x is always positive, which you could plug into ln. And so just, you get the cancellation equations, but you need to keep in mind the domains are different for each one. Okay? If you graph the exponential function, y equals e to the x, you get this. Okay, so that's the graph of y equals e to the x. And as you can see, that this limit tells you that the limit shows you the limit as x approaches negative infinity of e to the x is 0, because y equals 0 is a horizontal asymptote. And this arrow going up tells you that the limit illustrates how the limit as x approaches infinity of e to the x is plus infinity. And so these two limits are illustrated by the direction of the arrows in that graph. What's happening as x goes to plus infinity, what happens when x goes to minus infinity. Okay? That's on page 271. We have laws of exponents on the next page. So we know e to the x plus y equals e to the x times e to the y. E to the x minus y is equal to e to the x divided by e to the y. Okay? And e to the x raised to the r power is equal to e to the rx power. So we have our 3 laws of exponents. These are 3 laws of exponents. We also have the derivative, d dx, of e to the x equals e to the x. Okay, we have that equation also. Those are the cancellation equations. I mean, this was the definition of the inverse, this was the cancellation equations. Separating them. This is the inverse of ln x. Separate ideas here. This is the graph of the function, e to the x. Okay. These are the laws of exponents I put here. This is just separating these 7 ideas that I summed up on the board here. Okay, so you need to differentiate. Now, d dx of e to the x equals e to the x. Combined with the chain rule, you get d dx of e to the u, which is a function of x, is equal to e to the u times du dx. Okay, so that's this equation combined with the chain rule. You get that. So you need to know how to do that. Also, where u is a function of x. Okay. Also, the integral of e to the x dx is equal to e to the x plus c. You need to know that also. These are 2 more equations you need to know. All right. And so that sums up 5.3. All right. Okay, so let's keep going. Okay, so next is 5.4. So for 5.4, the first equation that comes up is a to the x equals e to the a ln x. I mean, e to the x ln a. Okay? So this is a way of expressing a to the x using e. Okay, we also have laws of exponents. So a to the x plus y is equal to a to the x times a to the y. A to the x minus y equals a to the x divided by a to the y. A to the x raised to the y is equal to a to the x times y. and AB to the x is equal to A to the x times B to the x. So these are 1, 2, 3, 4. These are 4 laws of exponents. So you have 4 laws of exponents there. We have that original equation there. Okay. We have d dx. The derivative of the function a to the x is equal to a to the x ln a. Okay, that's an important equation. You should know that. So you find the derivative of stuff. This equation combined with the chain rule says that d dx of a to the u, we use a function of x, is a to the u ln a times du dx. Okay, so that's this equation combined with the chain rule. U is a function of x. So you need to know that. Also, the graphs of 8 y equals a to the x. This is the graph of y equals a to the x if a is greater than 1. Okay, and then it looks like this if this is y equals a to the x if 0 is less than a, less than 1. So we're only considering positive a. Now if a equals 1, it's just a horizontal line. Okay? And so these are the graphs depending on where a is, what a is. Okay, that's a to the x, the graph a to the x. 2 cases, a greater than 1, a between 0 and 1, not including 0 and 1. We also have another formula, the integral of a to the x dx. From this formula, we'll tell you that this is equal to a to the x over ln of a plus c. That's another equation you should know. The power rule is there. If n is any real number, and f of x equals x to the n, then f prime of x equals n times x to the n minus 1. You need to know that. Okay. Here's another equation. Log base a of x equals y if and only if a to the y is equal to x. So you need to know that. The way I remember is a to the y is x. Kind of like visually looking at it. Okay. So these log base a and a to the y are inverse functions of each other. So the cancellation equations tell you that this is equal to that. And log base a of ax equals ax. That's the exponent of a. Okay, see those two functions cancel, and you end up with x again. So those are the cancellation equations for those 2 inverse functions there. The graphs of log base a are shown on page 279. You have the change of base formula. Log base a x equals ln x over ln of a. It's a change of base formula. You need to know that. And we have the derivative equation, d dx of log base ax is equal to 1 over x ln a. You need to know that also. Okay. Also expressing e as a limit, e is equal to I'll just point this out. E equals the limit as n per 1 plus 1 over n to the nth power. Okay. Good. It's e. Okay, so that's 5.4. So that's a sum area of 5.4. This is lots of ideas here on the board. Okay, these are the graphs over here. So you have, since I boxed everything, I guess I'll box this also. Or box or circled everything. So I have 1, 2, 3, 4, 6, 8, 11 separate ideas here. So you need to know these 11 things and some other things too. Okay? Okay, so let's keep going. so now we continue to 5.5. So for 5.5, it's about exponential growth and decay. And so the first equation they present to you on the first page of this section is that dy dt is equal to ky. And what that means is that the growth rate is proportional to the size of y. Okay, the rate of change of y is proportional to its size. Okay, and so this is called the law of natural growth if k is positive, and law of natural decay if k is negative. Okay, it's a differential equation because it's an equation involving a function y and one or more of its derivatives, in this case dy dt. Okay, so in page 284, the only solutions of this equation are the functions y of t is equal to y of 0, e to the kt. Okay, so these are the only solutions. These are all solutions. These are all the solutions to that differential equation. These are all the functions y you could plug in where you take the derivative of y and equals k times y. Okay, so it talks about population growth and radioactive decay. And so, and then at the end of the section, we talk about continuously compounded interest. And so the formula for that continuously compounded interest is a of t is equal to a of 0 times e to the rt. This is the initial amount, final amount. R is the rate, t is the time. Okay? This is for continuously compounded interest. So that's 5.5. Okay. Okay, so next is 5.6, which is on inverse trig functions. And so they're the trig functions sine, cosine, tan, secant, cosecant, cotangent. There's 6 trig functions we talk about generally. And so each of them have inverses. And so for instance, sine x has an inverse function, sine inverse x equals y, which is defined by sine inverse x equals y if and only if sine y is equal to x. Most functions, trig functions, are not usually one-to-one. So for instance, the sine function, which looks like this, it's periodic and it repeats, right? Periodic function. It's not a one-to-one function. It fails the horizontal line test. And so what you do is you restrict the domain from negative pi over 2 to pi over 2, and you get rid of everything else in the graph. So cut everything else out. You get rid of everything else, and so now you only have the domain from negative pi over 2 to pi over 2. Okay, so only that part of the graph. Okay, that's all we care about. And so now y equals sine x, where this is a negative pi over 2, where negative pi over 2 less than or equal to x less than or equal to pi over 2. This is important because this restricts the domain, right? We didn't say that. We don't write the restricted domain, then a function takes on what's called its natural domain, which means you could technically plug in any real number at the sign. And so without writing the explicit domain of a function, it assumes that your domain is every possible value you could plug into it. In this case would be the whole real line. And so we have to write the restriction in when we define this one-to-one sine function. Okay, so I write in the restricted domain, and I have this. If it passes the horizontal line test. So this has an inverse, and we denote it with that symbol. Another way to denote this function is arc sine x. This is the same function as that. It's just 2 different notations for the same function. That can be confusing. But arc sine x is the same as sine inverse x. It's just 2 different ways to write the same exact function. That's 2 different representations of the inverse function of sine. Okay, and sine has this restricted domain. Okay, so sine has its own inverse, sine inverse, okay, where we restrict the domain to this, okay? And so we have the cancellation equations for sine. Sine inverse of sine x equals x, and sine of sine inverse x is equal to x. Okay, so this is for x only in this subinterval. So this is for only these x values, because those are the only x's we plug into the restricted sine function. And this is for the x's we plug into sine inverse, which is from negative 1 to 1. Sine inverse is only from negative 1 to 1. That's because sine ranges from negative 1. The values of sine range from negative 1 to 1. The inverse function, you switch the domain and range. So for sine inverse, the domain of sine inverse is the range of sine. So this range of sine is from -1 to 1, which means the domain of sine inverse is from -1 to 1, which means the domain is the set of input values. Here, x is an input for sine inverse. So the inputs for sine inverse are the set of all values of sine, which is -1 to 1. Okay, and so these are the cancellation equations for sine and sine inverse. Okay, this is the graph of sine. Okay. Now, if you take the derivative of sine inverse, d dx of sine inverse x is equal to 1 over the square root of x squared minus 1. Oh, sorry, 1 over the square roots of 1 minus x squared. And this is only for -1 less than x, strictly less than x, less than 1. Okay, and so this is for sine inverse. This is what I would say about sine inverse. Alright. Okay, so for cosine, it also has an inverse function. So first, you take the graph of cosine and restrict its domain just from 0 to pi. So now the restricted domain is a different interval. Instead of from -pi over 2 to pi over 2, it's from 0 to pi. This is y equals cosine x, and I state the domain now, the restricted domain, and it's that. It's not the natural domain of cosine, it's now only from 0 to pi. And so with that, cosine x with this restricted domain passes the horizontal line test. That means it's invertible. And so now we can define y equals cosine inverse x to be equivalent to the statement x equals cosine y. Okay? Or, I guess putting emphasis on the cosine function, cosine y is equal to x. And this is for 0 less or equal to y less than or equal to pi. Y is the input for cosine, right? We said the input for cosine is from 0 to pi. It's not x. It's not x as a letter that goes from 0 to pi. It's the input of cosine that goes from 0 to pi. So here, y is the input of cosine, not x. X is the input for cosine inverse. So now the role of x has changed. While here x was the input of cosine, it's not the input of cosine now. Now it's the input of cosine inverse. Y is the input of cosine, which means y is what takes the values from 0 to pi for that cosine. Make sense? For that reason, that's the restricted cosine function. So this is our definition of cosine inverse. Okay? This is the definition of the cosine inverse function, right from the definition of an inverse of a function. Okay? And so this function satisfies the cancellation equations. Cosine inverse of cosine x is equal to x. Cosine of cosine inverse x is equal to x. These two functions cancel each other out. And this function this is for x. This is for 0 less or equal to x less or equal to pi, because x is the input of cosine. Here, this is for the inputs of cosine inverse, which means it's -1 less than x less than 1. And include the endpoints. Less or equal to. Okay? So the domain of cosine is from 0 to pi. The range of cosine is from -1 to 1. Okay? So that means the range of cosine is the domain of cosine inverse. And the domain of cosine inverse then are these x's. What these x's can be, that's from -1, including the endpoint. Okay, so that's why the domains are different for cosine and cosine inverse. Okay, so those are the cancellation equations for cosine and cosine inverse. And you could take the derivative of cosine inverse, d dx of cosine inverse x is equal to negative of 1 over the square root of 1 minus x squared. And this is for -1 less than x less than 1. Okay, so the derivative, we do not include the endpoints, -1, 1. It's strictly less than symbols here. Okay, so that's the equation for the derivative of cosine inverse, in which you can formulate, which we did talk about, and it's in the book. Okay? Well, we talked about it. Okay, so then, okay, so that's cosine inverse. A little bit about cosine inverse. Okay. Okay, so now for tan, we have tan inverse x equals y. That's if and only if tan of y equals x, right? So that's because tan inverse is the inverse of tan, okay? Our original tan function is restricted from negative pi over 2 to pi over 2. Okay, so we're restricting the domain of tan to negative pi over 2 to pi over 2, and its graph looks like that. This is y equals tan x from negative pi over 2 less than x less than pi over 2. All right, if this is for y for negative pi over 2 less than y less than pi over 2. That's because the y's are the inputs of tan, and the inputs of tan we're restricting to only strictly between negative pi over 2 and pi over 2, so it's a one-to-one function. If I extended the domain any more, I would not have a one-to-one function, okay? So if we could restrict it even, we don't want to restrict it even less, because we would have a one-to-one function if we restricted the domain even more. But we want our restricted tan function to attain all the values that tan originally did before we restricted it. So before, without restricting the domain of tan, it took on all real values, right? We restricted it just enough so it's a one-to-one, but we didn't restrict it too much so that we took away some of tan's values. Tan x with this restricted domain takes all the values that tan x did without the restricted domain. Okay? Okay, so that's y equals tan x. Now we have the inverse tan here. And so if you draw the graph of tan inverse, you just reflect that graph over the line y equals x. And what you get is that you get this horizontal looking thing. It's kind of easy to remember that it looks like this. And the asymptote here is pi over 2, and the asymptote there is negative pi over 2. This is y equals pi over 2, this is y equals negative pi over 2. And it looks like that, and it goes through the origin. Okay, this is the graph of y equals arc tan x, which is the same as tan inverse x, two different ways to say the same thing, the inverse of tan. And what this graph shows you is that the limit as x approaches negative infinity of tan inverse x is equal to negative pi over 2. And this arrow shows you this horizontal asymptote, the limit as x approaches infinity of tan inverse x is equal to positive pi over 2. Okay, so we get these limits by being able to draw this graph and seeing what the horizontal asymptote is here and here. Okay, so we have those limits, and dx of tan inverse x is equal to 1 over 1 plus x squared. So we get that derivative equation as well. Okay. We also have this graph. We had this graph already. I'm just going to draw that so that I kind of have everything circled. So I have these 5 concepts here on the board. This is about tan inverse. Okay, so you need to know these things, 5 things about tan inverse. Okay. Also, if you look on page 295, it gives a definition for cosecant inverse, secant inverse, and cotangent inverse. Also, there's a table of derivatives of inverse trig functions. Okay, so I want you to know the 6 of them, but you should special emphasis on the derivative of sine inverse x, the derivative of tan inverse x. Okay, so special emphasis on those 2. In fact, I'm going to write them down to make sure that I emphasize that point. Okay, so I want you to know dx of sine inverse x is equal to 1 over the square root of 1 minus x squared, and dx of tan inverse x is equal to 1 over 1 plus x squared. Okay? So you should know those. And there's 4 other ones too that are good to know. Okay. And you should be able to use these equations in combination with the chain rule. So for instance, ddx of sine inverse of u, where u is a function of x, would be 1 over the square root of 1 minus u squared times du dx. That's an example of using the derivative of an inverse trig function and combine with the chain rule. Okay? You would say u instead of an x, but then you multiply the end result by du dx. Okay? Also, at the end of 5.6, tells you the integral of 1 over square root of 1 minus x squared dx is equal to sine inverse x plus c. You should know that also. But that's directly from this derivative equation. The derivative of this equals this means that the general antiderivative of that is sine inverse x plus c. Okay, so knowing this means you know that. Also, knowing this second equation means you know that the integral of 1 over 1 plus x squared dx is equal to tan inverse x plus c. So be able to see how I could go from these two derivative equations to these two antiderivative equations. It's the opposite direction. Okay, and so what you should also know is this last equation in 5.6, which is the integral of 1 over x squared plus a squared dx is equal to 1 over a tan inverse of x over a plus c. Okay, so you should know the equation and you should know how to get that equation. Justification for it. You have to prove that. Okay? Okay, so these are 5 more things you should know about in 5.6. Okay? So that was a brief overview of chapter 5. Okay, key concepts of chapter 5. Okay, so the rest of this video, we're going to just do some more exercises and practice problems. Okay. Okay, good. The video's good. So if you go to your book, we go from 5.1 to 5.6 in this class, so we skip the other sections. But let's go to page 314. So go in your textbook on page 314. There's exercises at the end of chapter 5, chapter 5 review. 314. Okay, so let's do some problems here. Okay, let's do number 11. So number 11, part A, says e to the 2 ln 3. What does that equal? E to the 2 ln 3 is e is the same as 2 to the third power by the fact from our original equation in the chapter that said e to the x ln a is equal to a to the x. In this case, e to the 2 ln 3 is equal to 3 squared. It's actually 3 squared. Okay. So here the a goes here, so you see x is 2, a is 3, so it's 3 squared here. So that's a justification for this. That's equal to 3 squared, which is 9. Okay, part B. Alright, so that tells you this equal sign here. Okay. For part B, you have log base 10 of 25 plus log base 10 of 4. So log base 10 of 25 plus log base 10 of 4 is log base 10 of 25 times 4, which is log base 10 of 100, which is 2, because 10 squared is 100. So that equals 2. Okay. So this is by the laws of logarithms base 10, the first one. Okay, base A, where A is 10. That's the first one. Okay, so that's equal to 2. That's number 11. Let's do number 14. Okay, so for number 14, solve the equation for x, and let's do part B. So tan inverse x equals 1. Okay, well tan inverse x equals 1 implies that tan of 1 equals x. That's it. Okay, so that's 14b. let's do 17. 17 is differentiate. So we want to differentiate the function y equals ln of x ln x. So to differentiate, we're finding y prime. So y prime is equal to the derivative ln of a function, right? d dx of ln u is 1 over u times du dx. So ln of this, which is u, is 1 over x ln x times the derivative of x ln x. Okay, and so then that's equal to 1 over x ln x times the derivative of that. This is the first function, that's the second function. So it's the first function times the derivative of ln x, which is 1 over x, plus the second function, ln x, times the derivative of the first one, which is x. You get that, okay? And if you simplify this a little bit, you get x times 1 over x is 1, 1 plus ln x. So you get 1 plus ln x divided by x ln x. That's y prime. And so we differentiate y, for example, 17. Okay, we use this formula. We use that formula right here for that equal sign, right? The first equal sign in the solution. The u is x ln x. So ddx of ln of x ln x is 1 over x ln of x times the derivative of u, which is x ln x. All right, so that's 11, 14, and 17. Let's do some more. Okay, so differentiating another function. Let's do number 34. So 34, y is equal to e to the cosine x plus cosine of e to the x. Okay, so we want to differentiate this function, find y prime. Okay, so y prime is equal to derivative this plus derivative that. Derivative of e to cosine x, well, d dx of e to the u is equal to e to the u times du dx. Okay, where u is a function of x. Here, a function of x is cosine x. So here, u is cosine x. This is d dx of e to the u, which is e to the u times the derivative of u, which in this case is cosine x. So the derivative of e to cosine x is this times this, plus the derivative of cosine of e to the x, using the same idea here. Well, okay, so wait, actually, so d dx of cosine x is negative sine x, right? And you combine with the chain rule, d dx of cosine u is equal to negative sine u times du dx. Okay, so here u is a function of x. So d dx of cosine of e to the x is equal to negative, this is minus sine of e to the x times d dx of u, which is e to the x. So now we get that, okay? So I use these two equations, this one and this one, for this equal sign. All right, use this equation for the derivative of e to cosine x, which is this, and then I use this equation for the derivative of cosine v of x, which is that. So I'm going to erase this, because I need the space. And so now to finish this up, this is e to the cosine x times the derivative of cosine x, which is negative sine x, minus sine of e to the x times the derivative of e to the x, which is e to the x. And so y prime is equal to that. That's it. Okay? That's 34, differentiating y, given y. Let's keep going. so let's do 46. Okay, so for 46, it says find f prime in terms of g prime. Find f prime in terms of g prime. F of x equals g of e to the x. We want to find f prime in terms of g prime. So f prime of x is equal to the derivative of g at e of to the x times the derivative of e dx by the chain rule. And so this is equal to g prime of e to the x times e to the x. And so that means that f prime of x is equal to g prime of e of x times e of x, e to the x. And we found f prime in terms of g prime. Go down. Okay, that's 46. Okay, next, evaluate the limit. So let's do 63. All right, so for 63, evaluate the limit. So the limit as x approaches -3, no wait, as x approaches 3 from the left, of e to the 2 divided by x minus 3. Okay, so what's that limit? So I'm going to let u equal this, the e to the 2 over x minus 3. Let u equal 2 over x minus 3. Tongue twister, I guess. du, well, not du, anyway. So u equals 2 over x minus 3. So as x approaches 3 from the left, so as x approaches 3 from the left, I mean, here's 3, and here's x, and it's approaching 3 from the left. So its number is smaller than 3, approaching 3. If you take the numbers approaching 3 from the left and subtract 3, then you like shift it over by 3. And so now you're getting x's that approach, so x minus 3, which is a shift of x to left 3, is approaching 0 from the left. Okay, so if x is approaching 3 from the left, x minus 3 is approaching 0 from the left. So as x approaches 3 from the left, x minus 3 approaches 0 from the left. Well, if x minus 3 is approaching 0 to the left, 2 over x minus 3 is approaching 2 over 0 to the left. Well, 2 over 0 is infinity, but these are negatives here, so this is equal to negative infinity. So 2 over x minus 3 is approaching negative infinity. U is 2 over x minus 3. So that means u is approaching negative infinity as x approaches 3 from the left. So as x approaches 3 from the left, u is approaching negative infinity. And so this is equal to the limit as u approaches negative infinity of e to the u. That thing is u. Well, we know from the, you can either know it from the graph or you know it. I'm going to help you by illustrating it. This is the graph of y equals e to the, I'll use u, instead of x. Y equals e to u. Well, the limit as u approaches negative infinity is 0 of e to u. So the limit as u approaches negative e to u is 0. So the final answer there is 0. The limit as x approaches 3 from the left of e raised to the 2 over x minus 3 is 0. All right? Okay. So that's 63. Let's do some evaluating the integral question. So let's do let's do 81. 81 is evaluate the integral. So it's a definite integral from 0 to 1 of e to the x over 1 plus e to the 2x dx. Okay, so let u be the denominator. So let u equal 1 plus e to 2x. du is equal to 2e to the 2x dx. never mind. That's not a good u. Let's use this one. Let u equal e to the x. Du is e to the x dx. Okay, so in my head I was thinking about when you plugged in u equals e to 2x, you can't get rid of the du because there's an e to the x there. So let's do this. Let's focus on what works. Let u equal e to the x. Du is e to the x dx. So we can substitute here. So by substituting for definite integrals, we have, this is the integral of, well, e to the x dx is right here. So that's du over, so actually I'm going to put the du in front. E to the x dx is du. And this is 1 over 1 plus, u is e to the x, e to the 2x. E to the 2x is e to the x squared. So since u is e to the x, this is u squared. So this is 1 over 1 plus u squared du. But when x is 0, u is 1. And when x is 1, this is e. So this is equal to a definition from 1 to e of 1 over 1 plus u squared du. And this works perfectly because this is, we can use the fact that the integral of 1 over 1 plus x squared dx is equal to tan inverse x plus c. Okay? But instead for u. So this tells us that that equals tan inverse of u evaluated from the lower limit 1 to the upper limit e from this equation here. So this equation gives us that equal sign right there, that this is equal to that. Justification for that, saying this equals this, is this equation. Okay? So then, this is equal to tan inverse e minus tan inverse 1. And what's tan inverse of 1? That's root 2 over 2. Because tan of pi over 4 is 1. And so tan inverse of 1 is pi over 4. Okay, so tan of pi over 4 is 1. So tan inverse of 1 is pi over 4. So this is pi over 4. So this is equal to tan inverse of e minus pi over 4. And that's the answer. Okay? And so that differential is equal to tan inverse of e minus pi over 4. Okay, so that's the answer to that one. Okay, so let's do 84. 84 says the integral of cosine of ln x over x dx. What is that? I will let u equal ln x. Du is equal to 1 over x dx. That's because the ln x here is weird. Taking cosine of ln x is strange because of the ln x and usually it's cosine x, now it's cosine of ln x. We'll let u be ln x, du is 1 over x dx. And so now this is equal to the integral of cosine of u, because that's u, but then the x in the denominator is 1 over x dx, which is du. So you get cosine of u du. So that equals the integral of cosine u du, which is sine of u, plus c, and that's equal to sine of u, which is ln x, plus c. So that equals the sine of ln x plus c. So that differential is equal to sine of ln x plus c. All right? That's 84. Right, so after 84, do 89. Okay, so for 89, it says if f of x, you're given the f of x is equal to ln x plus tan inverse x. And the goal is to find f inverse prime of pi over 4. Okay, so let's find f inverse prime of pi over 4. So for this we use the inverse function theorem. So f inverse prime of pi over 4 is equal to 1 over f prime of f inverse of pi over 4. By the inverse function here. Okay, so we need to find what f inverse of pi over 4 is and to plug into there. Find the derivative of f and plug that number into f prime. Okay, so what value could we plug in here to get this equal to pi over 4? Let's plug in 1. F of 1 is equal to ln of 1 plus tan inverse 1. ln of 1 is 0. Plus tan inverse of 1, I mentioned in the other board, is pi over 4. So that's pi over 0 plus pi over 4, which is pi over 4. So f of 1 is pi over 4. That means f inverse of pi over 4 is 1. So this is equal to 1 over f prime of 1. The fact that f of 1 equals pi over 4 means that f inverse of pi over 4 is equal to 1. It's the opposite direction. Okay? So f inverse of pi over 4 is 1. So we can substitute that for 1 right there. So what's f prime of x? F prime of x is the derivative of that, which is 1 over x plus the derivative of tan inverse x, which is 1 over 1 plus x squared. So that's f prime of x. It's squared there. Okay? So now f prime of 1 is equal to 1 over 1 plus 1 over 1 plus 1 squared, which is 1 plus 1, which is 2. So f prime of 1 is 2. Oh, sorry. 1 over 1 plus 1. This is 1 plus, that's 1/2, right? Okay, so. So 1 plus 1/2 is 3/2. So f prime of 1 is 3/2. So f prime of 1 is 3/2. This is 1 over 3/2. And that's equal to 2/3. Right? 1 over a fraction is its reciprocal. So 1 over 3/2 is 2/3. So f inverse prime of pi over 4 is 2/3. Good. Okay, so now that's 89. Okay, so 83 is okay, so 83, the integral of e to the square root of x over the square root of x dx. So let's find this integral. So let u equal the square root of x, which in exponential form is x to the 1/2. du is equal to 1/2 x to the negative 1/2. That's the same dx. That's the same as 1 over 2 square root of x dx. So du is equal to 1 over 2 square root of x dx, given that u is the square root of x, x to the 1/2. Okay, so the u here, this is e to the u. The 1 over square root of x dx, we're missing a 2 in the denominator. So we can fix that by putting a 2 in the denominator. So this is equal to the integral of e to the square root of x over 2 square root of x dx. But if I put a 2 in the denominator, that means I'm multiplying by 1/2. So I fix that by also multiplying by 2. So this is equal to 2 times the integral of e to the u, and then 1 over 2 square root of x dx is du. So this is e to the u du. So this equals 2e to the u plus c, which is equals 2e to the square root of x plus c. And that's the final answer. So that's the answer to 83. Okay. Okay, so that's 83. Good. Okay, so let's do 77. So So for 77, it's the integral of 1 minus x over x squared dx. Okay, so let's find what this is. So I guess I'm going to multiply. There might be an easier way. This squared is 1 minus x over x times 1 minus x over x. This is equal to, in the numerator, 1 minus x times 1 minus x is 1 minus 2x plus x squared divided by x times x, which is x squared. So I just multiplied that out. And so this is equal to 1 over x squared minus 2 over x plus 1. Okay, so 1 minus x over x squared is equal to 1 over x squared minus 2 over x plus 1. So this is equal to the integral of that. I'm going to use exponential notation. So this is x to the negative 2 minus 2x to the negative 1 plus 1 dx. Okay, so I just took 1 minus x over x squared, and since it's equal to this, I plugged in, I'm writing this in exponential form, using exponents instead of using negative exponents, okay? So then this is now, using the evaluation theorem, this is equal to an antiderivative. That's an antiderivative of that. And antiderivative of x to the negative 2 is negative x to the negative 1. Antiderivative minus 2x to the negative 1 is minus 2 on x. And then antiderivative 1 is x. And so you take that, the sum of them. It's just a general antiderivative, not a definite integral. And so it's just that plus c. That's the general antiderivative. Okay, the most general antiderivative of 1 minus x over x squared. And that is the answer. Okay, so that's 77. Okay. Let's do 80. Okay, so for 80, you have a differential from 2 to 5 of dr over 1 plus 2r. So this one's easy. Let u equal 1 plus 2r. du equals 2 dr. This is equal to the integral of 1 over 1 plus 2r, and then there's a dr here, but we're missing a 2 here, so we put it there and we put a 1/2 on the outside. This is defined from 2 to 5. So this is equal to 1/2 the integral of 1 over u, 2 dr, which is du. And then when r is 2, you get u is 5. When r is 5, you get u is 11. And so this is equal to 1/2 ln of the absolute value of u evaluated from 5 to 11. And so that's equal to 1/2 times ln of 11 minus ln of 5. And that's equal to 1/2 ln of 11 over 5 by the log loss. And that's it. Okay, so that's number 80. Right? The absolute value of 11 is 11, the absolute value of 5 is 5. That's why the absolute value signs go with that. Okay, so that's 80. Go. Okay, let's do 62. 62 is, again, evaluate the limit. And we have the limit as x approaches infinity of e to the x minus x squared. And so let u equal x minus x squared. Okay, and we'll let u equal x minus x squared, this exponent here. Well, x minus x squared is also the same as equal to x times 1 minus x. Okay, well, as x approaches infinity, right? As x approaches infinity, this thing, obviously approaches infinity. As x approaches infinity, 1 minus x approaches negative infinity because of the negative x. The adding 1 doesn't matter. So we're multiplying a number tending to infinity by a number tending towards negative infinity. That means the product, x minus x squared, u, tends to negative infinity. Infinity times negative infinity is negative infinity. And so u tends to negative infinity as x tends to infinity. That's what that means. Okay, I'm going to leave it. That tends to infinity, that tends to negative infinity. Infinity times negative infinity is negative infinity. And so u tends to negative infinity as x tends to infinity. So this is equal to the limit as u approaches negative infinity of e to the u. And by the graph of e to the u, y equals e to the u, that's u, that's y. As u tends to negative infinity, e to u goes to 0, so that equals 0. So limit as x approaches infinity of x minus e to the x minus x squared is 0. All right? Okay. Okay, so let's do, let's do 79. So for 79, we have a differential from 0 to 1 of y e to negative 2y squared. Okay, so this is equal to, I'm gonna let u equal the exponent of e here. Let u equal negative 2y squared. So du is equal to negative 4y dy. So we have the y dy here, but what we're missing is the negative 4. So I'm going to put the negative 4 there. So you get e to negative 2y squared, and then the negative 4 goes there. And so if the negative 4 goes there and negative 1/4 goes there, negative 4 times negative 1/4 cancels to 1. This equals negative 1/4 the integral of e to the, well, that's u. E to the u, negative 4y dy is du. And when y is 0, u is 0. And when y is 1, you get u is negative 2. And so this equals, now I'm going to switch the limits of integration from 0 to negative 2 to negative 2 to 0. And then I'm going to get rid of the negative sign there. Okay? So this equals 1/4 times e to the u, evaluated from negative 2 to 0. Because e to u is the antiderivative itself, right? So this is equal to 1/4 times e to the 0 minus e to negative 2. This is equal to 1/4 times 1 minus 1 over e squared. And that's the answer. Okay? E to negative 2 is 1 over e squared. So that differential equals 1/4 times 1 minus 1 over e squared. Equals that. Okay, so 88 is the integral of x over the square root of 1 minus x to the 4th dx. Good. Okay, so we have this integral, and so we'll let u be what's inside the square root here. So let u equal 1 minus x to the 4th. Du equals negative 4x cubed dx. Okay, so we're missing a. Oh no, let's not make it that. So at first I thought to make it that because it's in the square roots, but let me make sure I put that in correctly. So this is the last evaluation question. This is difficult. The integral of 1 over the square root of 1